Hey everybody, this is our final demo video for the Precision DAQ package for Aerospace Applications Engine Capstone for 2024, part of the UW Electrical Engineering Department. My name is John Wick, and I'm this year's team lead. And the goal of this year's project was to develop a set of electronics which can be cheaply and easily built and integrated onto an aerospace application such as a drone. The picture shown here on our title slide is all of our electronics integrated onto the drone, streaming live data such as accelerometer data and GPS data into a single place. Our mentors were Sep Maxus and Gokul Nathan, and they're part of a startup called Fusion Flight. The rest of my teammates can introduce themselves.
I'm Ethan.
Hello, I'm Matthew Garcia.
Hi, I'm Maurice Huang.
I'm Matthew Lei.
I'm Hao Dongzhao.
As was established, our goal was to develop a set of aerospace electronics to improve the current sensing capabilities for aerospace applications. For us specifically, it was for unmanned aerial mobility, i.e. drones. The current industry solutions that are available are big and expensive and therefore wouldn't necessarily work with a drone. And part of the idea, again, as already established, is to make things much cheaper and better. So current industry solutions are sampling GPS at 1 hertz and IMU data at 10 hertz, which limits the ability to process the data available. So in order to come up with ways to solve this, we split up into 3 different sub-teams that each worked on our own separate technologies that we then integrated by the end of the project to work together.
All right, and to tackle that problem, we're gonna enhance the typical performance by 10x. So our sample GPS would now be at 10 hertz instead of the 1 hertz, and then our IMU or sensing systems will be formatting a rate of 100 hertz instead of the previous 10 hertz.
And then another requirement our system has is that it prioritizes real-time data acquisition, onboard storage capabilities, and wireless streaming, focusing on IMU and GPS data collection through industry standards by communication protocols.
And with all these varieties of sensors across our different teams, we're all going to fuse and integrate it into a single source. And we're also going to have our hardware draw less than 25 watts, and our overall product is going to cost less than $1,000 to manufacture.
As my teammates mentioned earlier, our team is split up into 3 sub-teams: the IMU team, GPS team, and our sensor team. We develop our board and functionality separately, but then we come up with the same on the same motherboard with the same solution. So we all developed through from breadboard testing, then went to firmware development, and then we send our daughter cards to manufacture. But our sensor team doesn't use the wired lines to transmit data, so they will not be on the motherboard. And you will see that in our demo next. Everybody is going to talk about their functionality and their boards.
Okay, this is our final demo live video showing all of our hardware in person.
And this is the motherboard that converts the drone battery voltage into the voltage that can be used by the daughter cards, which is 15 volts to 5 volts, and these are the buck converters on there. And here on the front, you can see these are the SPI and I2C communications that communicates between the daughter cards and the Raspberry Pi in the middle.
Here's showing the motherboard in action with all of our custom daughter cards on it. The Raspberry Pi is here in the middle. Here's the drone battery. Here's a live log of our output data. Here on the right is our GPS data, and then here on the left is our IMU data. If we unplug the IMU, we can see that the data goes out, and then if we plug it back in, we can see that the data gets fixed. And the purpose of this is to have a modular data system, and we can plug in a bunch of different types of daughter cards. The IMU is an example of one of our daughter cards. This board has different types of sensors on it and streams all this data at 100 hertz to the Raspberry Pi. This has sensors such as a magnetometer, accelerometers, gyroscopes, pressure sensors, and temperature sensors. This, combined with the GPS daughter card, provides multiple data streams in a single place on the Raspberry Pi. We developed all of this custom hardware ourselves, and yeah, this is it working.
As you can see here, we have our daughter card. It's connected to these antennas just for the sake of getting data quickly. On here, as you can see, we have 5 GPS sensors and our TNC microcontroller. This kind of communicates through UART. This collects, performs at a rate of 10 hertz. It collects 500 parameters per second. The types of data we collect is our experiment ID, our experiment time, data, time, location, weather, enclosure, longitude, latitude, satellite position, altitude, magnetic variation, horizontal, vertical, and position, dilution of precision, speed, and lastly, the seconds since fixed position of each of the 5 sensors. And as you can see here on the screen, we have our GPS data right in the middle. That kind of shows our data. And if we want to we also store our data into an iMicro SD card, so we can definitely move it on top of this our TNC and store it into any kind of device to access our GPS data.
And for full system integration for the GPS daughter card and the Raspberry Pi 5, we created custom firmware SPI communication protocol, which is industry standard. And this is a 32-bit SPI communication, 32-bit, and it communicates at 10 hertz to the Raspberry Pi, and full communication between the Raspberry Pi 5 and the TNC as shown.
So in our sensor team, we develop real-time data acquisition system to acquire a huge amount of data from every sensor pod simultaneously. And every sensor pod acquires data with a sampling rate of about 100 hertz. So about the same design, we mainly have a microcontroller, which is RB2040, with a data router on top of it for the backup of the data. And we also have the sensor, it includes a serial router and then a counter. So finally, we use the wire communication to finish the connection between the 4 sensor pods and the computer. And finally, the computer will receive a lot of data from the sensor pods, including the precision data and the magnetic field data. So because we only have used the accelerometer, also need to do some actual document regression or some variable translation or filters to process the original acceleration data for getting the precision information. So finally,
and as you can see, this is a live parametric plot of the magnetic field strength vectors. This is a magnet with a very strong magnet with a north pole and a south pole. I will move it over the sensors to demonstrate that this plot does work in real time. As you can see, now that I'm holding a south pole force above all 4 sensors, the south force is in the direction that the magnet is. If I flip it over, they experience a north force in the corresponding direction. As you can see, if I move it around, they should all experience varying degrees of strength in the X, Y, and Z directions. This plot is in real time.
Overall summary of our hardware and our engine capstone for the Precision DAQ Aerospace project. So next steps for our project are building a daughter card for all of these R sensor systems and incorporating it into our motherboard. Yep.